In astrophysical systems, major transport of heat occurs from radiation. Typically, we treat radiation in a diffusion approach, especially in the deep interiors of stars or planets. And here is the link between radiative transport and the diffusive treatment of a diverging flux in the temperature equation. Radiation can be described, among other things, by moment equations. And if we consider the moment equation for the time evolution of flux, that looks something like this. 1 over the speed of light squared times d by dt of f, the radiative flux, plus the divergence of the radiative pressure is equal to a variety of terms on the right-hand side. But if we restrict to the simplest case where motions are not important, it looks something like rho times the opacity kappa as a function of rho and t over the speed of light c times the radiative flux. And there are other terms of order, the speed of light or velocity of the flow over the speed of light, but if those are either very small or if there's just no motion at all, then we can maybe neglect these, which we do so for the sake of argument here. Okay, now let's simplify this sum. What we want to ultimately get to is an expression for the radiative flux. So let the time derivatives of the radiative flux go to 0, just for simplicity. Or equivalently, you could say that the 1 over c squared term on the d by dt, that might be driving this to be a very, very small term. So now we have something that looks like the divergence of the radiative pressure, which is equal to minus rho times our opacity kappa over c times f of r. So here's our radiative flux that we want to get. But now we have this crazy thing, the radiative pressure tensor. And in a set of moment equations, like radiative transport, and like comes up in classic kinetics, each successive moment equation depends on the next moment, and the radiative pressure tensor, 2 tensor here, is the next order of the expansion after the 1 tensor that's the radiative flux. And the only way we can make any progress is if we have some way of closing the system of equations. So we might make some simple lemma, like the Eddington approximation, to close our system of equations. Here we'll take the Eddington approximation, which says that the radiative pressure is proportional to the radiative energy density, E sub r, which is the 0th moment. So here's the first moment. Here's the 0th moment. And I'm labeling them by tensor order. And here's the second moment. So we say that the radiative pressure tensor, which is a 2 tensor, is proportional to the radiation energy, which is a scalar. That's a 0 tensor. And so there's a tensor identity linking them, what is called F, the Eddington factor. And this is called the Eddington approximation. Eddington tensor, technically. What is F? Well, therein lies a lot of magic. A simple approximation is that F is isotropic. The radiation goes everywhere in the same ways, and homogeneous. You don't know one direction from another, one place from another. If that's true, then F would be something like 1/3 for 3 dimensions times identity tensor. So what this looks like is a matrix with 1/3 and then zeros in the off diagonals, and 1/3 on the diagonals. Now, actual radiation doesn't quite work this way, but this gives you a reasonably good approximation in quite a few situations. And one could adapt F and change it from a 1/3 value to other values to capture, for example, a transition from opaqueness to transparency. And they're the classic Eddington-Milne atmospheres do this very thing. But we'll save that for a course on atmospheres. So let's come back to our closure here and our equations. So if we adopt this closure and write our equations in terms of our radiative energy density, then what we have is that minus rho times kappa, which is a function of rho and t, times the radiative flux divided by the speed of light c. This is equal to the divergence of P of r, which is equal to the divergence of the Eddington tensor times the radiative energy density. And in equilibrium, the radiative energy density, it's given by the temperature of the gas. If the radiation and the gas are well calibrated with each other in terms of their temperature. And in that case, E of r will take a special value of A T to the fourth, where this is the gas temperature. Gas temperature. Okay, so let's plug all that in and do a little bit of simplifying. So if I keep my terms here, so that's minus rho kappa times rho and t divided by c. And remember, this is opacity. This is not a fluid kappa thermal diffusion coefficient. This is a radiative opacity. The more of it there is, the harder it is for radiation to get through. The less of it is, the more transparent things are. Okay, so if we now plug things in here, and let's assume that f is a constant rather than a tensor, then we're going to get the following. We're going to get that, so we're going to start with div dot f a t to the fourth, and then this will itself be equal to pulling out f. This a here is a sub r, the radiation constant. We'll come back to it later. F a sub r. We could pull out our temperature here, T cubed, and a factor of 4 out front, and then the divergence contracts on the T and the identity tensor, and we have a grad T. Okay, so let's collect our terms we have so far. F of r is equal to minus 4f times a sub r times c divided by rho and kappa as a function of rho and t. We've got a t cubed in the numerator, and we've got a grad t here. All right. So what can we say of all of this? First of all, we see some interesting things. So first of all, we see that the radiative flux vector, it points down the temperature gradient. So it points from hot to cold because of the minus sign here in our equation. So the radiative flux goes from hot to cold. Okay, that's interesting. So F of R goes from hot to cold. We see some other things too. We see that the opacity shows up in the denominator. So if there is more opacity, there's less radiative flux. Let's write down those quick observations. So F of R goes from hot to cold, and if the opacity, remember this is the opacity, so I'll label that with rho and a t. If that goes up, then the radiative flux goes down, and vice versa. And that just says that if there's if it's more opaque, it's harder to get radiation through something. All right, let's do a little more manipulation of this form. So F, as I said, typically takes on a value of about a third, but we'll just leave it as an undefined constant for now. We're going to note one thing. We have this radiation constant floating around right now, And the radiation constant is related to another quantity that's maybe more familiar. The radiation constant is equal to the 4 times the sigma, or the Stefan-Boltzmann, sigma Stefan-Boltzmann, the Stefan-Boltzmann constant, divided by C. And this, the sigma here, this is the same one where if you have a black body, it has a flux that's sigma times T to the 4th. That's sigma Stefan-Boltzmann. And our radiation constant that's been floating around in our equations up here is tied to the Stefan-Boltzmann constant by this simple relationship. So since A shows up as a multiple of C, that suggests that we rewrite this in terms of the Stefan-Boltzmann constant, which cleans up our expression a bit. So now our new radiative flux expression, this is minus 4 times 4, that's 16, times F, which will typically be a third, times sigma Stefan-Boltzmann divided by rho times kappa as a function of rho and t times t cubed. All of this times grad t. In various places, you might see this described as a Fickian diffusion coefficient. Fickian diffusion coefficient, which just means that it's a diffusion coefficient in front of a gradient. And here we've written radiative transport in a Fickian diffusion fashion, which is a way it often gets modeled in simplified fluid dynamic systems. Let's put our vectors on top of our things here so we don't forget them. All right. So a couple more small steps. So if a Cranmer opacity is present, so if the opacity kappa is a Cranmer opacity law, so if Cranmer, which means we have a power law, a Cranmer-like opacity, then the opacity, this is equal to some k naught times rho divided by some reference value rho to the a, and this is then t over some reference t to the b, and these are for our power laws a and b. If we now put this into our radiative flux, we obtain an expression with the following form. If we put these in, we get that the radiative flux is equal to minus 16 times F times the Stefan-Boltzmann constant divided by kappa naught. So these are just a whole bunch of constants, and I'm going to gather together and times a rho naught here. I'm going to gather together various of our constants, so t naught cubed, and then it's times rho over rho naught to the minus 1, because of the rho that was in the denominator, plus a, and then t over t naught to the 3 minus b, and then all of this times the quantity grad t. So here we have some mighty diffusion coefficient, d as a function of rho and t. It's a nonlinear diffusion coefficient, and then that acts on a grad t. All right. All the vector information here comes from the gradient of t, and so in this simplification, the radiation only knows about the flux of energy going down the temperature gradient. Now, if we're in an equilibrium solution, then from the temperature equation, which takes the form d by dt of t equals terms, we'll do a proportional to so that we don't miss leading terms. It's the divergence of the radiative flux. And this is equal to 0 in equilibrium because the d by dt is 0. There's no change to the system. And if this is true, then the form of our system looks something broadly like this. It looks like the divergence of the quantity. So if we go up to our expression for the flux here, well, we can neglect all of our constants and we can worry just about our power law scalings here. So we have rho to the minus 1 plus a. So rho to the minus 1 plus a, and then t to the 3 plus b, or 3, excuse me, let's get our signs correct. 3 minus b, since the opacity shows up in the denominator, minus b, all times grad t. This is equal to 0. So here is our thermal equilibrium equation for a system with a Cramer opacity and where we're in a pure equilibrium solution and where the there's a tight linking of the radiative fluxes to the radiative energies. This leads to a system, as we saw in our Cramer opacity discussion, where we could have a hydrostatic equilibrium equation. So grad log P is minus G vector over RT, and we would solve that paired with a simple div dot rho to some alpha, T to some beta for power laws, grad T equals 0. And we now know that alpha should be minus 1 plus a quantity, and beta would be 3 minus b if the temperature and density dependence was being given entirely by Cramer-like radiative diffusion. The log p here, this can be turned, of course, into a grad log T plus grad log rho for an ideal gas, letting us solve the coupled system of equations.